So our opening keynote speaker is Professor Michael Weber, the Josey Centennial Professor in Energy Resources and Professor of Mechanical Engineering at University of Texas at Austin. Professor Weber is also the Chief Science and Technology Officer at ENGIE, a multinational electric utility company in Paris, France. Among his many accomplishments, Professor Weber is the author of the book titled Thirst for Power, Energy, Water, and Human Survival, published in 2016. In this book, he addresses the connection between Earth's most valuable resources and offers a hopeful approach toward a sustainable future. His latest book, Power Trip, The Story of Energy, was published in 2019 with a 6-part companion series that aired on PBS, Amazon Prime, and iTunes starting on Earth Day 2020. Today, he will give a big picture overview of global energy trends mixed in with anecdotes, historical snippets, and unexpected examples that will give a surprising look into the future of energy into his talk titled Power Trip, Transforming Past Societies to Address Today's Looming Crisis. Please join me in welcoming Professor Weber.
Thank you so much. I appreciate that and the opportunity to be part of this conversation today. I thought I'd just make remarks for maybe about 20 minutes so we have time for conversation and Q&A. I don't have any slides, just thought I would share some of my view of some of the things I've written, some of the ways I see the world. And I'll start by saying that I'm in my office at the University of Texas right now, and I plan to do this from home. I've been working from home for the last year or so, just like everybody, it feels like. But my power is out at home. I have an energy outage. This is the 6th power outage I've had in the last 9 months. So for whatever reason, my house has unreliable power. It's because we live in a wooded, hilly area of Austin, Texas. And every time there's a windstorm or an ice storm or a snowstorm, the trees lean or fall or break on the power lines and create all sorts of havoc. So I'm at my office doing this, which would be fine normally, but they're doing construction. And I think they're on lunch break right now, but there's been a racket like you wouldn't believe in my office. And so I almost had to do this from my phone in the car. I'm pleased to have an office right now. If it gets really too loud, I'll switch locations. But pleased to see so many of you here for the conversation. And I'll start by giving a little bit of my background, which is I studied aerospace engineering as an undergrad, really sort of interested in space exploration and rockets and the moon and all that kind of stuff. I think a lot of engineers are interested in space exploration one way or another, and was really pursuing that, and also got a liberal arts degree. So I studied liberal arts in addition to aerospace engineering. And as a freshman, I remember taking a class on the history of early civilization, about the foundational elements of society. And as a 19-year-old in the spring semester of my freshman year, I kind of had this realization that energy and water are the 2 fundamental ingredients of modern society. This is the thought I had. And I didn't really do anything with that, but I remember it and I noted it. And that became the basis of that book, Thirst for Power, Energy, Water, and Human Survival, that you mentioned as my first book, which is on these 2 foundational elements of society. I had that thought in 1990, and the book didn't come out until 2016. So sometimes a book takes 26 years to germinate. But I had this idea, or had this thought, I'm not the only one to have this thought, but I had the thought, energy and water are important, and kind of put it aside, didn't do much with it. Was an aerospace engineer, got involved in space stuff. And I went to NASA Ames Research Center. There's a NASA center in the San Francisco Bay Area. And I spent 2 summers as an undergraduate intern working on supersonic combustion ramjet propulsion systems for the National Aerospace Plane. This was a Reagan era initiative initially, although I was working there in the 90s, to create a plane that could fly so quickly and take off horizontally and land horizontally, could go from, say, the Pacific coast to Tokyo in 2 hours or something like that. So it's really cool to do some high-speed propulsion at NASA as a part of that. And we worked on the laser diagnostic sensors to measure the speed of the flow and the temperature of the flow and that kind of thing. But we were burning so much fuel to get this high-speed propulsion. And I really got introduced to energy through propulsion for aerospace applications. Kind of liked it. Went to Stanford for my master's and PhD in mechanical engineering, working on combustion systems, first for propulsion, but then just for combustion, developing sensors to measure the environmental pollution. And it slowly ingrained me into some awareness of the energy system, because it turns out that combustion is very important for our energy system. Something like 85% of the world's energy comes from burning something: oil, wood, coal, gas, cow dung, you name it. There's all sorts of things we're burning. The other 15% are from nuclear reactions or falling water or flowing wind or photons with solar panels. Most of our energy comes from burning something. And I was a combustion engineer, burning stuff and in the process polluting, but then developing sensors to measure the pollution. So I kind of got into energy from propulsion to combustion to pollution, and then understanding, oh wait, burning stuff's at the heart of the energy system. Sure is dirty. I wonder if we can make it better. So I went from aerospace to NASA to Stanford to combustion to laser diagnostics to measure environmental controls, and then became an industrial instruments guy making these sensors that would measure pollution. And then I became an energy guy. Like I looked up and said, oh, wait a sec, I'm an energy guy. I've been studying laser diagnostics or propulsion for 15 years. Turns out that's energy. And I had this transformation around 2005 when I was like, wait a second, energy is the most fundamental thing to society. I had that thought as a freshman in college, maybe it's time I do something with that, especially as that ties to water. So I just kind of redefined myself one day as like, I'm an energy guy. And I started to think a lot about energy. And the thing about energy is it's fundamental to society, but it's also hidden right in front of our eyes. It's in everything, right? It's enabling this conversation we're having virtually right now. It's in the light on my face. It's in the air conditioning in the room. It's in the wood of my desk. It's in the plastic. It's in the paper I'm holding. So energy is in everything, hidden right in front of our eyes. And this became kind of a powerful thought, like, okay, energy is everything. It's invisible. It's powerful. Perhaps it's worth studying. So I became an energy guy. And I would say that I have a lot of enthusiasm for energy because I think energy is fundamental, but and also kind of like magical. It brings light to dark and warmth to cold, or in Texas, cold to warmth. It gives us abundant food and comfortable buildings. It gives us abundant treated clean water. It gives us all sorts of things. And so this idea of energy as magical really is a motivating force for me, so to speak, of why I need to think about energy. And I would say that even there are some indirect ways the magical force of energy shows up in our cultural elements in our movies and books and that kind of thing. Let me give you a couple of examples. There's the story of the unicorn. Now today, people think of a unicorn as a billion-dollar tech startup, but the unicorn, the mythical one-horned creature, is a story that goes back hundreds of years to the Indus River Valley of Pakistan. And it's a magical creature, and people are fascinated by unicorns because there's never one been spotted, but somehow we're convinced they're around. But if you go back into the history of the unicorn stories and the old tapestries and this kind of thing, the power of the unicorn was not so much that it was rare. What was really great about the unicorn is its horn could rid a stream of water of its toxicity or of its poison. The horn could treat water. This is why the unicorn is amazing, is it can make water clean and safe to drink. And today, we use energy to do that. We use energy to treat the water to make it safe to drink. So we've replaced the magic mythical powers of the unicorn's horn with modern energy, electricity to pump the water through the membranes or whatever it is. So that's one way I think about it. Another example is from Greek mythology with the character Tantalus, in French, Tantal. So Tantalus misbehaved and was punished by the Greek gods. He was given eternal thirst and eternal hunger and placed in a pond of water below a fig tree. And as he would reach for the fig tree, the branch would bend out of reach. And as he reached down to get a drink of water, the water would recede out of reach. So the food and water were always just out of reach. And that's where we get the word tantalize from Tantalus, and having food and water always just out of reach. Well, today we use energy to bring water within reach. We can pump it thousands of miles and make it clean. We can refrigerate and make our food and have these supply chains that go thousands of miles. So we're using energy to overcome the power of the Greek gods to bring food and water within reach. That's another example. Let me give another example from Walt Disney's movies, Fantasia. I hope you've seen this. If you have not seen Fantasia, I recommend you see it. It is one of those old animated movies that actually has held up with time pretty well. A lot of these old animated movies don't hold up so well over time. They look pretty dated or awkward or insensitive in a variety of ways, but Fantasia is pretty interesting. And there's a classic scene there where Mickey Mouse plays the Sorcerer's Apprentice. So Mickey with the wizard hat, you've seen this in many ways. And what happens is the wizard gives Mickey a chore, and the chore is to go fetch water. And the water is heavy. He doesn't want to carry it. It's a lot of work. Imagine carrying a bucket of water. So a bucket of water might be 2.5 gallons, and a gallon is 8 pounds or something like this. Is like 20 pounds. So it's like tens of pounds if you have one in each hand. This is a lot of work to go get water and bring it upstairs. Mickey doesn't want to do it. He's kind of lazy. He's like, I'm going to use magic. And he uses magic to make a broom that will carry the water for him. But there's mayhem as the brooms keep multiplying, and then there's a flood. But the idea here is it takes a lot of work to lift water from the well upstairs to where we need it. Today, we use electric pumps and modern energy instead of magic to lift the water. Mickey used magic, we use electricity. And I'll give one last comment, and I'm sorry to obsess so much on the popular culture, but that tends to be the way I think about these things. There's this idea of medieval alchemists, like Rumpelstiltskin or others, who will take a popular, common, worthless material, hair, straw, lead, and turn it into something very valuable, like gold. And this is the story, right? That Rumpelstiltskin can turn straw hair into gold. In exchange, he does this for a captive prisoner's firstborn child, this kind of thing. And I would say that medieval alchemy is done on a continuous basis in the modern energy industry. Petroleum refineries are taking crude oil, which is worth less than lead. Lead's worth something like 50 cents a pound. Crude oil is worth like 20 cents a pound. Crude oil is not worth that much on a weight basis. And it turns it into high value products, gasoline, refined fuels, but chemicals, as well as perfumes like Chanel No. 5, which is worth more than gold. So we have this ability in the modern energy industry to take worthless things that are abundant and create high value things. So modern petrochemical facilities are like medieval alchemists in terms of their magic. So there's a lot of magic there. And I really sort of fascinated by it, the way we use energy instead of magic. There's even a kid's movie I just watched a year ago with my son. I can't remember the name of it. It's some adventure movie where they're using magic wands to light things up. And now we use electric lights, of course. So this happens all the time. And I would say that the magical part of it makes it kind of fun. But it's interesting because Arthur C. Clarke, the famous science fiction writer, said any sufficiently advanced technology is indistinguishable from magic. So I think of energy and high technology is kind of hand in hand, but magic is kind of like advanced technology and energy is kind of like magic. Therefore, energy and advanced technology go hand in hand. So that's sort of all just context for why I care about energy. The big picture for energy, the way I see it, is that energy done the right way makes us healthy, wealthy, and safe. Energy is good. It improves our life, but energy done the wrong way makes us sick, poor, and insecure. And this is the key thing, like energy is really good. It gives us so many comforts. It gives us mobility, it gives us freedoms, it gives us abundant food. It can also make us insecure. It can make the air dirty, it can make the water dirty. It can make us poor if there's volatility or price spikes or unavailability of the energy, this kind of thing. And so we might as well take the time to do energy the right way. It's not inherently always good. It can be bad if it's done badly, so let's do it the right way. And we should take the trouble to get smart on energy, and that's why I appreciate these kinds of conversations that you're organizing today. If I look at energy done the right way versus the wrong way, one way to think about it is the ways energy cuts across society. We tend to argue or think about energy in terms of coal or oil or gas or whatever. We talk about the forms of energy, or we talk about the trends, but really I think it's important to take the sectors and cut across and look at how energy is evolved in things like water and food and transportation and cities and wealth and security. And that's the way I wrote about it in Power Trip. And that Power Trip book you mentioned, Ginger, also has a 6-part documentary series on PBS, the same 6 parts. So there's an episode on water and food and cities and wealth and transportation and security. If we just look at water, the water and steam system in America is responsible for about 13% of our energy consumption. A lot of energy goes into treating, piping, chilling, pressurizing, heating water and getting it to where we need it in the form we want it. And a large fraction of that is for steam, but like 3 or 4% of national energy consumption is just for water heating in our homes and businesses. Think about how much energy that is. We have more energy embedded in our water heaters in our homes than Switzerland uses for an entire year for all of their purposes. So it's a lot of energy goes into water heating. Something like, by the way, the flip of that is we have a lot of energy for water. We have a lot of water for energy as well. Like half our water use is for the energy system. Most of that is for power plant cooling, but it's also for irrigating biofuels, leaching minerals out for rare earth metals, sort of dust control and things at coal mines. We use water for water flooding or hydraulic fracturing for oil and gas production. We use water to float barges and ships to carry energy products to market. So we use water for the energy system. We use energy for the water system. And this interlinking dependence can be good. It can increase performance. It can also be bad. With Winter Storm Uri in Texas in February, which I endured, I had 2.5 days without power, 4 days without heat, and 5 days with a boil water notification after that. Water failures, freezing water, broke pumps and equipment at power plants. It froze off the gas system. That created energy shortage. That made routine blackouts, which turned off the power to the water system. And then our water got dirty. So it just was a cascading series of failures. So the interdependence of energy water can be good in terms of lifting the systems up. It can be bad in terms of bringing them down. That's what we experienced. And if you have interest in it, I'm happy to talk in more detail about what happened in Texas. How is it the most energy abundant location in the world had an energy shortage in February? Happy to talk about that. That's water. The food system uses about 10% of national energy consumption. 1% of national energy consumption is the energy into the food itself. Then the next 9% or so are for the agrochemicals, the diesel for the tractors, the propane for drying crops, the diesel for the trucks to move the food to market, the electricity for refrigeration, the energy for cooking, and then the energy to do the waste disposal of all the food waste. So there's a lot of energy in the food system. Unfortunately, we throw away like 1/4 to 1/2 of our edible food, not even like the inedible food, but the edible food we're throwing away as significantly. And there's enough energy embedded in the edible food we throw away. As Americans, with so much food abundance, we just kind of overserve and then throw it away. We could power entire countries like Sweden for an entire year. It's like an entire rich, large European country could be powered up for a year just on the energy embedded in our food waste, which is really incredible. So the food system is very energy intensive. And now we're talking about using food for energy with like corn for ethanol and soy for biodiesel or palm oil for biodiesel, that kind of thing. It's really incredible, these interconnections. Transportation is now the biggest energy consumer and emitter in America. It's like 28% of our energy consumption. Cities are 40%. Wealth and energy go hand in hand, and security in energy have a complex relationship where energy can be a cause of, enabler, and target of war, but also a great source of our capabilities for our defense. So energy lets our military and fighting forces be more capable, but it also creates vulnerabilities because we might buy our energy from a country who hates us, and they use those proceeds from those energy sales to attack us, as has happened before in American history. That's kind of the way I see it. There's these 6 parts of food, water, cities, transportation, and wealth and security, and we got to do it the right way. Well, all of this system I just mentioned where energy is coming across the entire society is changing because of 6 demographic trends, which is population growth, economic growth, industrialization, urbanization, electrification, and motorization. I'll repeat those in a second, but there's 6 demographic trends and 3 technology trends and 1 two-sided challenge. So the 6 demographic trends are population growth and economic growth. There's more of us and we're getting richer, which means that energy consumption is growing globally. There's industrialization and urbanization, which means we're moving from farm to factory, from rural areas to cities. So we're changing how much we consume and where we consume it and what we're consuming it for. Instead of agriculture, it's for factories. And then we have the rise of motorization and electrification. As people get rich, they really prefer mobility and electricity. Electricity gives us the creature comforts of wealth, which are in addition to water treatment and food preservation, computers, and lighting. And then mobility is one of the great joys of freedom that energy gives us, lets us move farther, faster. And that's what the world wants. And so as we go through those 6 demographic trends, how much we consume, where we consume it, and what we're consuming for is changing. Everything's changing, it seems like. Well, overlaid on top of those 6 demographic trends are 3 technology trends: increasing efficiency of goods and services. It takes less energy to light the light bulb now, and cars become more efficient, and we put less mass into things as they get lighter. And that's a good trend. A second trend is increasing information intensity or increasing data intensity. So we're using less energy and mass for products and services, but we're using more data. And actually, the more data or information enables the efficiency, which is a good news trend. And the third trend is increasing decentralization or decreasing centralization, especially for the power sector. We might have rooftop solar or community storage or things like that, rather than just large power plants far away. So those 3 technology trends of increasing efficiency, increasing information intensity, and increasing decentralization on top of those 6 demographic trends mean everything's changing for energy, all within the context of this two-sided challenge of how do we increase access to energy for the billion people in the world who don't have access to modern forms of energy, while decreasing the impacts for the 7 billion who do have access. So the 3 tech trends and 6 demographic trends are wrapped up in the two-sided challenge. This means it's just a mess. Everything's changing, and this is why we have some companies having board shakeups, like ExxonMobil just yesterday lost a 3rd board seat. So ExxonMobil, the giant oil and gas, is changing. Electricity companies seem to be on the rise. Oil and gas is bumpy. Renewables are doing great. And so there's just like this transition going on. And what does that mean? And I would say the good news is we've been through energy transitions before, so we kind of know it takes us to a better place, at least it usually has in the past. With lighting, we went from solid fuels like torches or candles to liquid fuels like whale oil or kerosene to gaseous fuels like gas lighting, and now electric lighting. And even within electric lighting, we've gone from arc lighting to incandescent lighting to fluorescent lighting to LEDs. So we've had a transition within lighting technologies. Same thing with mobility, went from muscle power like walking or riding an animal or rowing to wind power with sailboats to steam power fueled up by coal to liquid fuels like kerosene for jet fuel or gasoline for cars to now electric cars and other things, although people are going back to like e-bikes and scooters and walking. And also for heating, gone from solid fuels like biomass or cow dung, we've mentioned before, for heating or coal, to fuel oil for heating, to gas, electricity. So we've gone through transitions a few times. We know we can do it. This is just another one. The prior transitions give us some lessons. Those transitions have been good for the most part. Let's think of the transition from wood to coal. Wood was a dominant source of building materials, but also heat for millennia. But around 1850, coal really rose in prominence and overtook around 1880 wood in the United States. Coal had more energy density and burned more cleanly, and it was cheaper and closer to market. And this was a good news story because we had cut down most of the forests in the eastern half of the United States. We had deforested so extensively. The rise of coal actually allowed us to let those trees grow back. So if you go to New England today, it's very wooded in New England. That is second growth forest. That is regrowth. That is not the forest that was there 200 years ago because we cut those forests down. So that's just sort of a weird thought for us that coal saved the forest, because today with strip mining and acid rain, we think of coal as a threat to the forest. But 150 years ago, coal was good for the forest. Same kind of idea with oil and whales. We used whale oil for lighting, the whale oil we could burn in a whale oil lamp, but we started to run out of whales. We killed so many whales. And it became more expensive to get the whales. We had to go farther away to get them. And it became like 2-year journeys in the Pacific to get the whales, to get the whale oil. And then kerosene comes along in the 1850s, late 1859 and on. And if you get kerosene for lighting, the kerosene was cheaper than whale oil. It was cleaner, it didn't smell as bad, it was closer to market. So we went to kerosene and we quit whaling, and the whale populations have recovered. So oil was good for the whales, which is different than what we think today, because we think of offshore production today as a threat to whales. But coal was good for the forest. Oil was good for the whales. That's an interesting lesson, because it means the solutions for energy might become tomorrow's problems, or today's problems might have been yesterday's solutions, is one way to think about that. So we need to be mindful as we come up with new solutions that they're solving one problem. Maybe we're solving the problem of carbon dioxide emissions of coal and oil today, that we don't introduce other problems, or that we are doing what we can to minimize those problems at least. So the transitions have happened. They've been good news for us. There are other lessons. These transitions can be slow. Let me give some examples. If you look at the United States, the primary energy conversion we do in the United States, 60%, 3/5 of our primary energy conversion goes through 4 devices: a steam turbine, a gas turbine, a gasoline engine, or a diesel engine. Those 4 devices are 60% of our energy conversions. The rest of the energy conversions are like boilers and burners and cooking hobs and some chemicals production, and that's about it. Like most of the stuff is just burning it for heat or cooking. 60% is primary energy conversion through a turbine or an engine. And that's kind of interesting, because those 4 devices were invented as recently as the 1890s. The gas turbine made its debut in 1791, the steam turbine in 1884, the gasoline engine in 1876, and the diesel engine in 1893. We are running the entire modern global economy on 4 devices invented as recently as 130 years ago. And I think that's just like stunning, that we haven't had really any breakthroughs or big innovations in energy. Even nuclear power is an innovation as recently as the 1940s, uses a steam turbine, which is this older innovation. So it feels like there's time for something new and some innovation. Maybe we could go to something like wind turbines, which were first demonstrated in 1888 for electricity, or solar panels, which were first demonstrated in 1893. We could go to something really cool like fuel cells, which were first demonstrated in 1839. I guess you're getting the story now. All these things are old ideas. Even electric vehicles, James Prescott Joule in 1839 anticipated that electric machinery would outpace steam or heat-based machinery. So there's no new ideas. There's a couple, here's a new idea. The idea of using wind power to make fuels. We're talking about today, like, let's have wind powered electric turbine, make electricity, to split water to get hydrogen and then give it fuel. So it's sort of power to fuel, or wind to fuel. That seems like a good idea. Turns out the Dutch were doing something like that in the 1700s, using wind power to crush oil seeds to get oil they would burn for heat and illumination. So even wind to fuels has been around for a couple hundred years. At ENGIE, we have a really cool demonstration blending hydrogen with natural gas in our pipelines in Dunkirk to use for burners and other lights and other things. And we have the world record for this. We blended 20% hydrogen with gas and had the first demonstration of that. We're really proud. I was just reading and stumbled across this. Gaston Leroux, the French author, in 1910 wrote a book called Phantom of the Opera. You might know the musical. And in the book in 1910, he talks about blending hydrogen with natural gas to change the brightness of the stage lighting at the Paris Opera House. So even cool ideas like hydrogen blending with gas have been around for like 111 years. It just kind of makes you shake my head. It's like, okay, it feels like we're ready for some new innovation. We need some new ideas. We can't just depend on French authors and German chemists or whatever from the 1800s. We need to really make a step forward. And that gives me some optimism that with students who are more innovative and creative today than in my generation, that we'll have some solutions. And we really need to move towards these options. These lessons of the technology transitions tell us a couple things. One is we can do a transition. We've done it before. We can do it. Another is usually it takes us to cleaner, higher performing, more affordable options, which is good news. Another lesson is yesterday's solutions might be tomorrow's problems, like I mentioned with oil and coal. The other lessons, there aren't many new ideas, so we need some good thinkers out there. And the last one is transitions take time, they take decades. We better get started, so we better get hopping. So I'll stop there so we have time for some Q&A and some conversation, but I just want to say, I think energy is fundamental. I think it's important to everything we care about. It cuts across every part of society. It's kind of magical. It's kind of hidden. We might as well take the time to do it right. An energy transition is upon us. Let's do it in a thoughtful way so that we can manage the transition with the least negative impact possible and the most positive outcomes. And that's going to take a lot of good ideas. So I'll stop there. Thank you so much for inviting me to speak. And I hope there might be some questions and conversation.
All right. Thank you very much, Michael.
Yeah.
We'll open the floor for questions. If you want to type them in the chat or use the raise hand function, I'll call on you. I just want to start off with a comment is that we've used PowerTrip for several semesters now in our energy studies minor capstone class. And this year, the students were asked to develop a slide. So instead of going chapter by chapter, we wanted them to kind of look at the book as a whole and figure out what meant the most to them. And we actually had them talk about doing energy the right way and doing energy the wrong way. And so what the different outcomes would be of that. And it was a really great turnout. So
I'd love to hear that. That's great. Thanks for telling me that. That's great.
So the first question that's come in is, if you had a pile of money to invest in future energy technologies, where would you invest it?
So great question. And I actually am in a position where I can invest in startups here and there. So I'm making these decisions for myself in real time. There are a couple areas that seem really promising. Now, the first question might be, well, whose money is it? Is it like government money, policy money? Is it venture money? Is it money that needs to make a profit or not? But the best place to invest money as a society is usually in efficiency and conservation, because the dollars we put into that have the biggest bang for the buck in terms of savings. There's a lot of low-hanging fruit in terms of the avoided energy consumption. And so there's a lot of opportunity to invest really in a positive way for society on efficiency and consumption and on conservation. Now, the business model that can be tricky because sometimes it's better done as a system rather than as an individual investor, unless it's a particular technology. But as a society, that's where we should start. And I do that personally at my house. My wife is an architect and we remodeled. We put in more efficient air conditioner and triple pane windows and devices and that kind of thing. And investing more in efficiency at home pays for itself. So I think that's the best place to put money. And I think that's a great option. The other things that are pretty exciting, I think, are and more difficult are in the low carbon fuels or green gases or carbon neutral fuels. So if we think of the logic of society, the first thing we should do is energy efficiency and conservation, which I just mentioned. The second thing we should do is electrify as much as we can, at least within reason. There's a lot of things we can electrify, like light duty surface vehicle transportation, some temperate heating. There's some things we can do with electricity that really effectively. And then there's some things that are hard to use electricity for, like chemicals or aviation or industrial heat for cement and steel, and maybe long distance trucking or shipping and this kind of thing. And so we'll probably have to use fuels for those. And the question is, which fuels? Is it biofuels or hydrogen carriers? But there's this high value, hard to abate part of society that's hard to electrify, for which we'll need fuels. And whoever can crack the nut on getting low carbon fuels there, which might be hydrogen or hydrogen carriers, something like that, there's a lot of money to be made, because those will be hard to reach parts of society with the other options. And so that's where I'm putting some of my own effort and money, is around low carbon fuels. Like, what are some novel pathways to making hydrogen? And hydrogen, by the way, is a great fuel. You can use it for anything. You can make heat, you can use it for chemicals, you can make electricity, but it's hard to make, move, and store. So if you want to think about where to invest research money or your own personal money, I would think around hydrogen production, storage, and movement is an opportunity. And there's many more, by the way. There's a lot of things we can do with data to make the system smarter, more resilient, to get some savings. But in terms of my personal effort, I'm doing a lot of systems analysis on the grid and also looking more closely at hydrogen these days.
All right, thank you. The next question is that people are looking a lot into geothermal being the next big thing. And, you know, you'd be able to take workers and technologies that were developed in the oil fields and transfer it to this geotechnology. So what do you think about for the future of geothermal in the U.S. energy mix?
I think geothermal is one of those great resources that has been underutilized for a variety of reasons. We know it works because countries like Iceland depend on it and do great with it. It is a 24/7, 365-day-a-year source. There might be some geothermal fields that deplete or play out over decades or centuries, but for the most part, there's unlimited potential in the world. When we run out of geothermal resource, we have bigger problems as a planet. So there's lots of it. It's just a matter of how far you got to drill to reach it. In some places it's closer. So Iceland's one where it comes to the surface naturally. There are parts of like near Turin in Italy where geothermal has been harnessed for over a century, but also in California, there's some really good, Nevada as well, some really good geothermal resources closer to volcanoes, like where you have seismic activity volcanoes, the geothermal resources might be closer to the surface. You can also drill for it. You don't have to wait for it to come to the surface. And we have such great capability in oil and gas to do really advanced drilling where you can hit the hot spot just as you need it. And in fact, we've been drilling for oil and gas for well over 100 years. We often find hot water by accident. What if we look for the hot water on purpose and just aimed for it and then get the hotter hot spots? Then we could use that geothermal as baseload power. It's low carbon, it's reliable, this kind of thing. And it can be a great sort of complement to wind and solar and hydro and some of the other resources we have. So geothermal should take off, especially in the mountain west where it's closer to the surface, or also where you have oil and gas activity, maybe Oklahoma, Louisiana, and Texas. So there's some opportunities for it. And it's everywhere. It's even in Florida. You just got to drill deeper for it or the resource isn't quite as high. So at least not as hot per kilometer. So it's a great opportunity. And we're seeing a lot of growth in that at ENGIE. We just opened up and commissioned a 100 megawatt geothermal plant in Indonesia and other places. It's a suitable replacement for coal in terms of its round the clock performance or even nuclear. So I think geothermal will grow. What's interesting is even though we don't have a lot of geothermal activity in the United States in terms of new construction, the United States does have more geothermal than any other country. We're bigger at it than people realize. Almost all of that's in California. And I'm starting to see some venture investments in this space. Breakthrough Energy Ventures, the sort of billionaires, $2 billion fund with Bill Gates and other billionaires put money into some geothermal companies, and there are others. So I think it's a big opportunity, and especially if you have good resource close to the surface. As a way to repurpose oil and gas skills seems like a natural fit. Drilling for oil and gas and drilling for heat, these are maybe slightly different geologies, but same kind of skill set. So I think that would be a really great way to manage some of the social justice issues of labor disruption and transition.
So talking about that Texas energy crisis, what are some other possible vulnerabilities that you think are out there?
A big one is around the grid. So I like electricity because it offers a lot of performance benefits to modern society. We have a lot of things that depend on electricity, and electricity is easy to decarbonize compared to other sectors. So electricity is really valuable for us. Therefore, we should electrify more parts of society. The downside is, as we become more dependent on electricity, when it fails, it really disrupts life. And so I've been without power for the last day. That's why I'm here in my office. I just had a 2-day power outage a week ago, and then a 2.5-day power outage in February. Like, I've had so many power outages, and it's so disruptive because my modern life depends on electric power, and our modern civilization depends on electric power. So as we electrify more, we become more dependent. We really need to be reliable. And the reliability problems tend to be around the wires and poles, not the power plants themselves. Although in Winter Storm Uri in February, we had the big freeze in Texas, the power plants themselves also froze up, but usually the problem is with the wires and poles. And we tend to string them above ground so that they're vulnerable to the wind and can fall down, or they get ice that coats on them and causes them to break, or they spark a wildfire in California. There's just all sorts of challenges. And I think that's the weak point of the system, is what the transmission and distribution looks like. And that implies we need to do it in a better way, build closer to market if we can, bury the lines underground, build more microgrids or other solutions, have more storage on the system. We're getting these long sprawling systems that we have to turn off preemptively for wildfires or break during winter storms, and that's no good. The example of this happens to oil and gas is with the Colonial Pipeline, the cyber attack a couple weeks ago. One pipeline responsible for like half the refined fuels on the East Coast can't operate because of a cyber attack. And so it wasn't the refinery that failed or the gas pumps that failed, it was the distribution between the two is a problem. That's often the weak point for electricity. I think we need to invest more in that area. It looks like the Biden-Harris administration's big infrastructure plan, it was like a $2 trillion infrastructure plan, is thinking about modernizing and hardening the grid. I think that's a big vulnerability. So we got to think about that for sure.
All right, so what are your thoughts on some solar thermal arrays?
I am not as excited about solar thermal compared to solar panels. The inherent advantage of solar thermal is it uses working fluids, molten salts, or heat transfer fluids, or has hot rocks. It has storage built in, which is a huge advantage for solar thermal. And it really gives you, I don't know, another 4 to 10 hours of storage. So you get almost baseload performance out of solar thermal, maybe 20 hours a day instead of 8 hours a day you might get for solar panels. So that's the good news for solar thermal. The bad news is it tends to be much more much more expensive, it's a lot more capital. And you have to build it in the desert, and you often need water for cooling or something, but deserts don't tend to have a lot of water. So there's other of these cost problems. And meanwhile, solar panels have dropped like 90% in cost in the last 10 to 15 years. So solar panels become so cheap and so easy to bolt on to rooftops or parking lots and other places that you don't need the big solar thermal the way we thought we did, especially if you have declining costs for batteries as well. So I'm less optimistic about solar thermal today. It just looks expensive compared to solar panels, especially with the declines in battery prices or the availability of gas for backup. So I think it's going to struggle. That doesn't mean it'll go to zero. It just seems like the growth of solar panels, these photovoltaic panels, is going to continue outpacing solar thermal dramatically.
All right. What do you use to keep up on your energy news? Is there a favorite newsletter or website that you check regularly?
This is a great question. So I consume a lot of news, yet I feel like I never know enough. And so I just constantly say, but I use Twitter for a lot of this. I follow a lot of energy journalists on Twitter. I follow a lot of energy analysts and researchers and professors on Twitter. And I get a lot of information from Twitter. So Twitter also has like the rage and all the politics and yelling and that kind of thing. And I try not to do that too much, although I've done my fair share. But I use it for this whole energy Twitter community. It gives me a lot of leads on great information. So that's my go-to place every day. I also read a variety intentionally of magazines and newspapers. For my local news, it's the Austin American-Statesman. So I read the local paper and the statewide paper, the Texas Tribune. My national papers are the Wall Street Journal and New York Times. I have a couple, like a liberal website and a conservative website, more like blog services and clipping services I go to. And then I use The Economist for my international news, which is a weekly news magazine. So between the local news at Austin American-Statesman, Texas, national, and then international Economist, I get a pretty good view. And the international view is particularly helpful because The Economist has a sort of a snarky, sarcastic attitude, which is sometimes helpful for Americans to say, okay, what do the Brits think about us? Because they'll speak more honestly than we will in many cases. So that's been helpful for me. And so that's like my news sources. But frankly, I learn more. Oh, and then, of course, I'm sorry, back up. The authoritative reports from the IEA and the EIA and Department of Energy. There are a lot of authoritative reports. I can't read them all, but I try to at least be aware of what's being written. So at least I'll see the headline and know what topics are on people's mind. And those are good sources for information. But I tend to talk to a lot of people, and I feel like I get better insights from talking to humans than reading reports. And then those insights in hypotheses almost from talking to humans tell me what reports I should go read. There's so many reports to read, but through conversation, I'll learn what's really happening. And so I'll speak to inventors and investors and venture funds and government policymakers and journalists and students and faculty. I just try to talk to everybody. And I feel like I learn more from humans than from the written word, which might be more sort of a reflection of how I learn and how I study. But I feel like that's a good way to pick up on what's going on, just because people will tell you what they're doing. And if you ask them about the work, they'll say, here's what I'm working on. And then you get it, you can kind of paint the complete picture if you talk to enough people.
Excellent, thank you. So is there going to be a third book?
Yes, actually it already came out, but I've got another book. So I got a book that came out in October of 2020, my COVID book with Roger Duncan. And that book is on the future of energy. Roger Duncan was the CEO of Austin Energy for many years. And we wrote a book on the future of energy. And it came out in 2020. And the funny thing is we started it in 2008. It took us 12 years to write a book on the future of energy. And we joked that by the time we're done, it'd be a book on the past of energy because things were happening so fast. So things that were really innovative in 2008, like drones, were standard fare by 2020. But we did that book on the future of energy, really looking at fundamental trends. So Power Trip was more like the past of energy with a little bit on the future. This is more like, okay, where are we going? What's next? So that book came out. I just had a book come out a month ago with a co-author called From Athletics to Engineering, 8 Ways to Support Diversity, Equity, and Inclusion for All. And so I wrote that with Johnny Johnson, who was in the NFL for 10 years, professional football player, and then a very successful businessman and entrepreneur after that. And he's been working with my engineering students for over a decade on executive coaching and different life skills that aren't methodological or engineering based. And we wrote this together on diversity, equity, inclusion, because it feels like we're at a point in America where we have to decide whether we want an exclusivist society or an inclusive one. Do we want everyone to have a place in society or not? And Johnny and I both feel pretty strongly that we all deserve a place in society. And even in the field with athletics and in engineering, we have these challenges with DEI. So that book just came out a month ago. And it leveraged a lot of my engineering experience, but isn't specific to energy. But I have two more books I'm working on in energy that might come out someday. One is Hunger for Power, on the intersection of food and energy, really expanding chapter 2 from Power Trip into a book-length issue, as well as a collection of essays. I've written something like, I don't know, 175 op-eds and essays and articles. So I'm gonna do a collection of essays at some point. So I've got a couple more energy books cooking. I still want to write a book on energy in cities and energy and national security. I've got, I don't know, like 20 books I've started. It's not hard to start a book, it's hard to finish a book. And so I'll see which ones I can pick up from all of those and move them forward.
All right, fantastic. If there are no other questions from the audience, I'll just ask you one final question.
Sure.
What would be kind of your final take-home message for people?
I think that my final take-home message for people is that energy cuts across everything we care about in society. You name it, public health, cybersecurity, there's an energy angle, either as an enabler or a target or whatever it is of it. So energy is worth studying because it cuts across everything. But then I would also urge humans, everyone on the call, myself included, my students, everyone, because energy is so broad and cuts across everything, there's value in us being broad thinkers. There's so much pressure in academia to be narrow and deep, to narrow what we do and go deeper with it. And from depth comes breakthroughs, but from range or breadth comes impact. And I think energy naturally aligns itself with breadth because it cuts across society, but there are technical depth issues. You might be a real expert on rock fracture mechanics or fuel cell design or something like that. That depth is valuable and really critical to society, but the breadth really helps it bring it forward to the markets or to policymakers. And so energy is inherently broad. We energy people should also be broad. We should get out of our discipline and study other things, read other books, read some literature, study other disciplines where we can. And I think that would help us be better energy researchers and educators and policymakers and decision makers. So I think the breadth and range of energy aligns naturally with who we should be as humans. And I think that will help us get some better solutions in place.
All right, thank you very much. We really appreciate you coming and chatting with us today and joining us for our research symposium.
Yeah, my pleasure. Thank you so much for inviting me.
So for now, we will take a 15-minute break and we will start back at 2:40.